Okay, so if you've had a sneak preview of the notes from this morning, I had a bit of a pickle with Friday's classes. So instead of canceling, I know that would be so nice of me, right? What I'm gonna do is I'm gonna have the 8 a.m. It's only 50 minutes, right? So the 8 a.m. block is gonna go on Zoom, but then I'll post the video from that. So you could watch it during our regular class time if you want to, or kind of anytime, or you're welcome to join on Zoom 8 a.m. on Friday, kind of get it over with. I know you might have classes and stuff, but or sleeping to do, I don't know. But I'll post the video and for you to watch whenever you'd like.
Wait, do we not have class on Friday? Or is this a double class?
Well, I teach the same thing in the morning, and then I have you guys and I say it all over again. So, and then I have something, so I won't be able to do this class. So then I'm just gonna leverage the morning one. If that makes sense.
Just this Friday? Or
Just this Friday.
Okay.
Yeah. So this Friday, which I'm pretty sure is October 7th. 4th today. Okay, good. Good, because that's what I said this morning. So this Friday, right? I can't make it to our class, and I have to do the other one on Zoom. So either meet me on Zoom at 8 o'clock, 8 to 8:50. Okay, so that's not our regular time, of course, or watch the video on your own time. It'll be the same amount of time as our regular section. So if you wanted to kind of use that time, that's great. But you're all adults, so you can figure that out on your own. Okay, so hello, new phone, new this. So hopefully that makes sense. Sorry about that. But it is a long weekend, and another long weekend. It's crazy. Oh, it's too many long weekends, Emily. I can't handle it. I know. No one's complaining about that though. Last long weekend. All right. So a little bit of review. We talked about the complement of an event, which is basically the event not happening, right? And so the complement of an event, we established that the probability, and how we denote the complement is usually by a superscript C. So the probability of the complement of A is 1 minus the probability of A. You can rearrange those, solve for whatever you'd like, right? The probability of A plus the probability of not A has to equal 1, right? And so you can move those all around. If A is passing this course and I tell you the probability of A is 80%, then your mind automatically goes, okay, so that's 0.8, 1 minus 0.8 is 0.2. The probability of me failing this course is 20%, right? I made that up, but it's incredible what our minds do already, right? And so, right, if I tell you one thing and then you can quickly get to the other thing, right? And that's the complement of an event. We don't really call it that usually. Time to make sure that I am recording and I'm sharing my screen, so that helps, I guess. Okay. So the complement, we don't really call it the complement typically, but now we do. Okay. We also talked about independence, And there were a couple of things that we could do with regards to independence. So independence means that the probability of an event doesn't depend on the outcome of another event, right? And so things like if I flip a coin, knowing that it landed on heads doesn't impact the probability of if I roll a die, then I get a 6, right? It doesn't change that probability. Same thing if I flip a coin and then I flip a coin again, knowing that I got even 100 tails in a row does not affect the probability of the next one being tails, right? And so because they're independent events. So the probability of an event does not depend on another event happening / not happening, right? Depending on the scenario. Okay. And we said that, okay, well, if A and B are independent, then the probability of A and B can be calculated by just the probability of A times the probability of B. This was an important part of that, right, is if. So if they're independent, then we can use this formula, right? If they're not independent, that's what we're going to talk about today. Well, what do I do if they're not independent, right? And we use this a couple of different ways. We could say, okay, well, if I know that A and B are independent, then, and if I need the probability of A and B, then I can just multiply them together and I can find that probability, right? Usually it's the other way around, right? So we'll have all three of these probabilities, all these components. So then what we can do is we can multiply the probability of A times the probability of B. And if it equals the probability of A and B, then A and B are independent, right? So we kind of use this formula, but in reverse, right? So there's kind of two ways that we can use this formula. I'll call that the end of the review because now we're going to talk about, okay, well, what if A and B are not independent? Okay, so, all right. Here they come. I knew you guys would come. I just didn't know when. So section 3.2 is conditional probability. Oh, can't write it all today. Conditional probability is just not independent events, right? So now knowing that one thing has happened affects the probability of another thing happening, right? So for example, if I have a deck of cards, right? And I tell you, okay, well, I've drawn 3 hearts already, right? Then that knowing that I've pulled out 3 hearts and they're no longer in this deck that I'm choosing from, right? That affects the probability of drawing a heart, right? Every time I remove one, then there's one less heart in the deck, right? So it becomes 12 out of 52, 11 out of 52, 10 out of 52, right? As I remove each of these hearts. So now all of a sudden, these probabilities are dependent on what happened, right? And so conditional probability results when two events are not independent of each other. Results when two events are not independent of each other. And I'll highlight that not independent. Another way that we could say this is knowing the outcome of one event, right, affects the probability of the other. Knowing the outcome of one event affects the probability of the other. Affects the probability of the other. That's a natural way of thinking about it. One thing that I'm going to change is instead of saying knowing, right, because that's kind of a common term that we use, right? I want you to start saying, okay, well, given. So given some information about something that's already happened, then what's the probability of that other thing, right? So that is conditional probability. Okay. And it all hinges on this, given some outcome, right? What's the probability of the other outcome? Okay. Some terminology that we'll introduce first. And I'm going to use the voting example from September 22nd, this one, which we've used before. And the reason I want to use it is because I want to show you that you've already solved problems with conditional probabilities. We just didn't call them that. Right. So from the voting example, from September 22nd. We said, okay, well, we have all this information about how people vote and how they feel about the citizenship option. So what I'm going to do is I'm going to develop some shorthand here and say that, okay, what if I use a V for how they vote, right? So V is either C, M, or L. V is going to be how people vote. And then this event is, I'll call it C because I think I've called it that in the past, which is how they feel about citizenship. And we have option 1, 2, 3, or 4. Right. How people feel about citizenship. Yeah. Part of the question that we solved together asked, okay, well, just looking at these percentages, right? We solved some problems together. And then finally, political ideology and views on immigration appear to be either dependent or independent. So now we can attach kind of formulas to this, right? And so we said, well, it looks like they're dependent. And why? Because the percentages across the groups, and in this case, we were talking about in favor of the citizenship option, right? We would expect them to be kind of mirroring how people vote, but that's not really the case here, right? And so we had these different percentages, and that was our argument for them being dependent on each other, right? Knowing that someone votes liberal, right? That affects the probability that they're in favor of the citizenship option, right? And so here, on September 22nd, we said B and C are dependent events. Right? I like the shorthand. Otherwise, it's so wordy. B and C are dependent events. Okay. And maybe I'll follow up with, since the percentage in favor of, maybe I'll call it option 1 of option I, right? Following the same notation. Across the political ideologies was very different from each other, right? Across the political ideologies were very different from each other. So these are the raw counts, right? So before we do anything, usually we convert these to just probabilities or proportions, right? And so if we divide each cell in the contingency table by the total sample size, right? So each one of these we can divide by 1240 in this case, right? And then we can get a table of proportions instead. Proportions are probabilities, right? So that's a good step in the right direction here. But if we divide each cell in the contingency table by n, and in this case, n is 1240, okay, we will have a table of proportions. Okay. Which I went ahead and did it kind of a cheater way of doing it. We're only going to use some of these, so you don't need to jot these all down yet, but right, so if I take, for example, 59 divided by 1240, I decided to go to 5 decimal places, right? Then I get 0.04758, right? And then I went across and I took each cell divided by 1240. And yes, I did it by hand. So silly, right? Only because otherwise I would have had to enter the table anyways. What a waste of time. So, and then we can find these overall probabilities in the margins, right? And just some terminology here. The margin, so the total probabilities in the rows and the columns, we call those marginal probabilities, whereas these guys in the kind of the meat and potatoes of the table, those are our joint probabilities, right? They're joint because they're the probability of voting in favor of applying for citizenship as well as voting conservative, right? So it's that overlap right? This and this.
Could you please join the marginal and joint probability?
Yes. Do you mean like this or no? So these are your marginal probabilities. Or do you mean like a Venn diagram?
No. Could you please repeat?
Oh, repeat. I can do one better. I'll even steal the thing. But first, let's write. These are marginal probabilities. And then these are what we call joint probabilities. And stealing from, oh. They said it best. Oops. If the probability is based on a single variable, it's the marginal probability, right? And we even answered questions about this, right? What's the probability of being in favor of option 1? We took the total, the row total divided by 1240, and we found the probability 0.31693, right? What's the probability of voting conservative, right? That's the column total 0.39516, right? And so as soon as it's just about one thing, it's the marginal probability. But then the probability of two outcomes happening at the same time, that's a joint probability, right? Being in favor of option 2, for example, and voting moderate, the probability is 0.11774. Right? You'll notice as you add these up across the rows, you get the same totals, right? So you don't even need the marginal totals. You can just add up and find the margins by summing across the rows and also summing across the columns. And then of course, the total has to be 1 because I'm dividing everything by this number. But because I only kept 5 decimal places, there was some rounding. So I'm going to go ahead and say that 0.9999 is close enough to 1, roughly 1. But you do want to make sure that they do get kind of close. But because I rounded, right, that's okay. But you do need it to be very close. Yeah. Good. So let's see here. Let's see. As a made up example, right? What if I want to find the probability of voting liberal? Find the probability technically of a randomly selected person voting liberal, but I'm going to shorthand this and say, okay, well, we called this variable V, right? How do they vote? So then the probability that V equals L, oh, that's confusing. You had to be here, right? How about that? So the probability of voting liberal just from above, right, is the overall probability of 0.20806. 0.20806. What about the probability of being in favor of option I, applying for citizenship? Find the probability of being in favor of option I. Let's call that the probability that C equals option I. Well, applying for citizenship overall had a probability of 0.31693. 0.31693. You could be giving just the fractions, right? Those total counts over 1240. I'm just giving the rounded values, right? The proportions, the rounded proportions. But what if I wanted to know if these actually are independent or dependent on each other, right? We can use that formula. We can apply that independence formula as long as I know the probability that of voting liberal and choosing option 1. Okay, so then find the probability, and now I'm gonna cheat a little bit. V equals liberal and C equals option 1 or option I. Yeah. So now that I have this table of probabilities, right, that's the joint probability. So they have to be in favor of option 1 and they have to vote liberal. So that's 0.14758. 14758. Okay. So now we can see if these things are independent or not. We already said that they're not independent, right? And we had kind of justification for that. But now we can apply the mathematical formula just to see if we were right or not. Okay. So we can use these probabilities to determine whether B and C are independent. Right, we already said that they're not. We said they're dependent, right? And one thing, so here I'm kind of glossing over, right, how people vote. Is it independent of how they feel about citizenship, right? Because if one of those categories is off, right, so not equal, then the rest of the categories will also be off, right? So now we can say the probability that B is liberal and C is option I. I want to know, is it equal to, wasn't a very beautiful question mark, a little bit better, right? And I'm going to highlight that because I don't know if that's true or not. Does it equal the probability that B is liberal times the probability that C is option I? I know all these probabilities, right? I have 0.14758. Does it equal 0.20806 times 0.31693? Once I go through here, have it with the rounded values. So here we go. 0.20806 times 0.31693 I get roughly 0.0659404558, which is not 0.14758. So that's why we can say that these events are not independent. Therefore, these events are not independent. Right? They have to be exactly equal. Now, there is some rounding involved here, but there shouldn't be enough to make a difference, right? That's why I kept 5 decimal places, right? And so this is definitely not the same, but even if they're relatively close, right, they have to be equal, okay, in order to be considered independent. So now we've confirmed it, right? We said, no, because it looks like these percentages, they're not evenly distributed here across the categories. And that was our kind of gut reaction. But now we have the mathematical reason why they're not independent. Okay. Which means that, okay, if I want to know, just in general, if I want to know the probability of A and B, then this shows me that I can't rely on just the probability of A times the probability of B, right? If they're not independent, right? And that's what I've been emphasizing this whole time, right? They have to be independent for this to work. So now, right, if we didn't have this to check against, if we just went ahead and multiplied these values, we'd be using the wrong number, right? So we need some way to deal with that, right? When we have events that are not independent. Okay. So, these events will require conditional probabilities. And I'm going to steal the little blurb. Okay. So I'm kind of giving you the formula, and then we'll pick it apart, and then we'll use it. Okay. So a conditional probability of outcome A given condition B, how we're going to solve that is with this formula. But first, there's some notation here that we need to get a handle on. Okay. So this we read as the probability of A. So far, so good. But then there's this vertical bar, and we read that as given. Okay. Given B. Okay. So this given is that vertical bar. And notice that the given is here as well. And I guess given is the vertical bar. Okay, now that's not so bad, right? So now the probability of A given B, so knowing that B has already happened, now I'm going to have this conditional probability of A. Okay. And how we solve for that is we're going to need the probability of A and B, which, okay, we've done that before, we've seen that before, and then divided by the probability of B. Now you don't have to memorize this formula. I'll give it to you, of course, but I do find that it's helpful if you kind of try to memorize it a little bit, right? And so how I kind of remember it is the probability of A given B, if I just write it out, is the probability of the first and the second, right? Probability of A and B. So kind of first and the second. And then divided by the probability of B, right? The probability that B happened, right? Because I know that B happened, but it only happened with some probability, right? And so here, just kind of read it like that. So now, right, if I rearrange this formula, I have a formula for the probability of A and B that incorporates a conditional probability. All right, so I can rearrange these. These are just placeholders for three things, right? So as long as I follow order of operations, right, I can multiply the probability of B over to the left-hand side, and then I'll have the probability of A and B. So we can rearrange this formula. To find the probability of A and B is the probability of A given B times the probability of B. I guess I get a little sneaky because I use the equal sign as kind of a revolving door, and I always have whatever I want to solve for on the left. But I've really just multiplied the probability of B over to this side. So this looks similar, right? Not quite the same. But if we think about that special case when A and B are independent, well, then the probability of A given B, well, it doesn't care. If A and B are independent, then all of a sudden the probability of A given B is just the probability of A, right? And so that brings us back to that special case where we started, right? So here, if A and B are independent, it's like some beeping, and it sounds a lot like my egg cooker. I know, who needs an egg cooker? What a stupid thing. They're really handy though. I need a rice cooker, I need an egg cooker. Just only cooking one thing. I need a cook. That'd be great. Right? Because if they're independent, then all of a sudden, right, it doesn't matter what happened with B, right? Then the probability of A given B is just the probability of A, right? So then that brings us back to that special case, right? Which brings us back to the special case where A and B are independent. The probability of A and B is just the probability of A times the probability of B. All right. So just like you were safe to just go ahead and use the general addition rule, which said the probability of A or B is the probability of A plus the probability of B, and then subtract the overlap of probability of A and B, right? Because if there's no overlap, then that just goes to 0, right? So same deal. Now, if you wanted to, you could focus on just this formula, right? And then develop that special case if they're independent. Yeah. So let's apply this formula to a question that we've already solved, right? But using the formula instead. So again, I'm going to use that voting example. We didn't even know we were doing all this fancy stuff, right? We can solve these problems. If we just have the table, we can solve these problems however you'd like, right? And so we don't need this, but I need to tell you about it. So from the voting example, and maybe I should put it on a fresh page down here. September 22nd. Remember this tricky one, part D. Oh, it looks the same as the other part, or is, right, looks the same as C, but they're different. Okay. So now, right, what percent of these Tampa, Florida voters who identify themselves as conservatives are also in favor of the citizenship option? So we can reword this question, right, in terms of a conditional probability instead, right? So we can reword this question. Right? Because we said, okay, well, they have to be conservatives, right? So given that someone votes conservative, right, what's the probability that they're in favor of option 1 or option I? Keep saying that. Given that someone votes conservative, what is the probability of being in favor of option I? What is the probability of being in favor of option I? Okay. So even though the given part of the question is usually what we're given first, right? It's actually the second part of the formula, right? So you don't want to get confused, right? You want to read it as the probability of A given B. So given that someone votes conservative is the second part. So we want to find the probability that someone, in terms of the citizenship, C is option I, given that V is conservative. And just for more shorthand here, how about I say this, I'm going to summarize as C equals I and V equals, well, there's no way around it, V equals C. But when you're in it, it's obvious which one belongs where. Okay, so now I have this conditional probability, right, given some information. So now, of course, you can use the formula if you want to, right? The probability of A given B is the probability of A and B divided by the probability of B. So I'm going to start there, and I'm just going to write this out in terms of that fraction. So the probability that C equals I and V equals C. Those two things happening together, divided by the probability that V equals C overall. I have both of those probabilities from my table of proportions. So first things first, the probability of being in favor of option I and voting conservative is 0.04758. I better jot that down, 0.04758. Divided by the total probability of voting conservative, which is 0.39516. .39156. Again, you could just use the fractions, right? 59 over 1240 divided by 490 over 1240, cancel the fractions, right? But I'm going to use the decimal. 0.04758 divided by 0.39156. I get 0.1215139,442. It's not going to be quite the same because I rounded, right? So here, these are rounded values. So if I try to match it, it's not quite the same. So if you use the real fractions, you would get the same value, right? 12.04. Right. This is slightly different due to rounding. Yeah. But overall, we get the same thing. So you've already solved conditional probabilities. It's just we need to apply it in this kind of formula framework. Now, it was only like 5 minutes ago, but I can't remember if I brought in I did not. I said it, but I didn't bring in the general multiplication rule. Toss it in here. I should have put it when I introduced it, right? When we rearranged that conditional probability formula, multiplied it by the P of B to find the probability of A and B, right? But here it is. Okay, good. So what if we don't have a table? Oh, that doesn't feel good, does it? What? No table. I want to do this example. Now, if you haven't read the smallpox example, they have a huge example where they go through and they pick things apart. And the general idea of it, right, is it's from 1721, so a really long time ago, and it's about smallpox in Boston. So then we're talking about, okay, were people inoculated and did they live or die, right? Yes or no, lived, died, right? And so we can make this table, but now let's pretend that we don't have this table. That's where I want to jump in. And you just take my word for this. Oh, too big. So we've got this smallpox data set, and let's say we're only given two pieces of information, right? And so the first piece is that 96.08% of residents were not inoculated, right? Inoculated is essentially vaccinated, if that's easier to think about. And I actually don't know the difference. Any biologists here? I don't know. Feels like someone's on it. But until then, and 85.88% of the residents who were not inoculated, right? So now we're talking about a subset of these, of the population, ended up surviving, right? How could we compute the probability that a resident was not inoculated and lived? Okay. So now, okay, we've got two pieces of information, and I would say the hardest part of this is recognizing that we're given a conditional probability, right? Ironically, because it's given, right? So here, this is a conditional probability. So of those who were not inoculated, right? So given that they were not inoculated, 85.88 of those survived, right? So it's going to be easier if we set up some variables, some placeholders. So if we because we're talking about inoculated and not inoculated. So I be inoculated, which I'm just going to write vaccinated if that, because we're constantly talking about vaccinated now. So not vaccinated. Oh my gosh. And surviving, right? Lived, died is either survived or didn't survive, right? They're all dead now, but because it was 1721. Unless I'm missing something. Maybe the smallpox is the key. So S be a placeholder for survived, right? And then we can talk about they survived or they did not survive. Right? So what we want to do is we want to find the probability that a resident was not inoculated and lived, right? So here we want to find the probability that they were not inoculated and survived. Right. It says lived, but that is survived. Yeah. Okay, so now let's figure out, surely we have all the components we need to solve this thing, of course, but let's pick apart the question and assign some probability notation, right? And so we're given 96.08% of residents were not inoculated, right? So the probability of not being inoculated was 0.9608. Remember, you have to convert it to the proportion, right? The decimal in order to use it for math, but also probabilities or proportions. Now the tricky one, right? So you can kind of cross this part off. We've dealt with that. So now 85.88% of the residents who were not inoculated ended up surviving. Yes.
Can we first solve the equation using that percentage sign and at the end we divided by 100? Would it give the same answer?
It won't, because of how proportion or how decimals work when you multiply them, right? So if you take say 0.5, well, that was a bad example. 0.25 times 0.25, right, is not the same as 25 times 25. So 0.25 times 0.25 is 0.06. So 0.25 times 0.25 is 0.0625, whereas of course 25 times 25 is 625. So even if you multiplied by 100, it doesn't work. Right, because this would be 6.25. I guess, no, gets lost. You'd have to divide by 100 twice. Yeah, which would be the same as using the proportion. Like, no, it doesn't work, but now I'm like, it would, you just have to do it twice. So if you wanted to, I guess you could, but no. Good. Okay. So this conditional probability, and that's going to take a lot of practice, right? Reading these and recognizing that this is a conditional probability. That's not easy, right? And so this is our first one. So I'm giving it to you, right? And so what we're given is the probability of surviving, right? Given that they were not inoculated, right? So given that they were not inoculated is 0.8588. Yeah. So one thing that I could do is I could multiply these together, right? Because I recognize this pattern of A given B and then the probability of B, right? If I kind of map them like that. But then I'm kind of halted because then I have the probability of B and A, but that is the same, right? So around the and, right? A and B is the same as B and A. However, A given B is not the same as B given A, right? So order matters in the given, right? But not around the and, right? And so, or the probability of S and not inoculated, right? And I only swap those, you don't have to, I only swap those so that we can match to the formula, right? Because in general, if I have the probability of A and B is the probability of A given B times the probability of B. If I'm trying to map this back and forth to my variables, right? That's the probability of S and not inoculated. Which is the probability of S given not inoculated, right? Just matching them up, times the probability of not inoculated. I have those components. So now I have 0.8588 times 0.9608, which is roughly 0.825135504. So the probability of surviving and not being inoculated is 82.51% overall, right? Okay, so a little bit finicky when you're reading these things. What do I know? What do I know? Right? But with practice, you'll start to see, okay, there's going to be some given information and then some probabilities. You have to map it. So one way that we can organize information for these problems is using a tree diagram. Now, a tree diagram, just like a Venn diagram, you don't need to use it, but I do find that it's really helpful in kind of organizing all the information that you're given. So to help us organize information, for probability questions, I'm going to say, especially with either conditional probabilities for sure, but also if you have consecutive events, which could happen, right? I toss a coin, I roll a die, right? And then I could have these consecutive events, right? Remember, we drew the slots, right? But what we'll see is we could have drawn a tree as well, okay? And so I'll say especially with conditional or consecutive events, right? So if I know that you got an A on the midterm, right? If we write a midterm and a final, right? Knowing that someone got an A on the midterm means there's a higher probability that they get an A on the final, right? But overall, that's a small group of people, right? And so those would be kind of consecutive as well as conditional events. So especially with conditional or consecutive, oh, I can't. I wanted to throw a Q in there. I don't think that's right. But where? We can use a tree diagram. So what I want to do before, we could use these probabilities, but I found that it got a little hairy. So in general, I just want to outline what a tree diagram is going to look like. Now there can be any number of branches, right? It's a tree, so there's branches, and we can have any number of layers. But just in general, a tree diagram looks like this. So let's say I have only two possible outcomes for A. Right. So here I'm going to call this event A. That's going to get confusing. Nope, it's okay. We can handle it. Right. So either A happened or it didn't. Right. So A can be writing the midterm. You got an A on the midterm or you didn't get an A on the midterm. Right. That kind of thing. Then, right, so all the possible outcomes are outlined in the branches. And of course, there can be more branches, but it's going to get pretty crowded pretty quickly. So I'm just going to focus on two, and then we'll do an example with 3 at the top. Okay, so then if we talk about event B, and notice I like to end them at the same spot here, because then I can talk about the layers, right? Event A is one layer, event B is another layer, the second layer. So then, and I'm being very, very generic, right? A, B. Regardless of what happened here, either A happened, well then A happened and B happened, or A happened and B didn't happen, right? So then B happened or B didn't happen. Same thing here, A didn't happen, but B can still happen or B cannot happen, right? And so we've got all these possible outcomes kind of drawn out. So now, we've got these consecutive events. First event A happened, then event B. Okay. Maybe event A is passing the midterm, right? And maybe event B is passing the final exam, right? You either passed the midterm or you didn't, right? There's either, if you pass the midterm, you can pass the final, or you can pass the midterm and not pass the final, or you can not pass the midterm but pass the final. You can not pass the midterm and not pass the final, and that's bad news, right? So here we've listed all these possible outcomes. Below here, I rarely use the proper notation. So here's where I'm going to introduce the proper notation. But below here, you would write the probability that A happens. And usually I just use the decimal, right? Or the proportion. And the probability that A doesn't happen. Right? Then, from the question, you'll be given these conditional probabilities, right? Because the probability of B, but I had to go down the A branch, right? And so here, below B, you're going to have the probability of B given that A happened. So that is a conditional probability. Same thing here. The probability that B doesn't happen given that A already happened. Same thing here, the probability that B given A doesn't happen, and the probability of not B given A, not A. So now, what we can do is, just in general, if you want the probability of A and B, right, you can multiply down the branch. Right, and so the probabilities at the end of each branch, if you multiply down, is the probability of A and B, A and not B, right? A, not A and B, not A and not B. Okay. So often I'll summarize it just by A, B, A, not B, not A, B, not A, not B. But technically, what's going on down here is the probability of A and B is the probability of A times the probability of B given A. Rearrange those, right? I have the proper formula for the conditional probabilities, right? But this is just by multiplying down the branch. By multiplying down the branch. So usually what I do is I end up just going through, I set up the branches, right? I set up all the probabilities, and then I go through and I find the probability at the end of each branch just by multiplying down. Even if the question doesn't require it, I think it's a good exercise, because what we want to make sure is that at the end of each of these, those are all the possible outcomes, right? So the total should be 1. Right? And so here, the sum of these probabilities must be 1. Yeah. So remember when we said, when you're saying and, right, A and B, you're going to multiply. But then what if I just want to know what's the probability of B happening, right? So, well, B happened in this one branch, but also in this branch. right? So it can happen here or here. So as soon as you're saying or, then you add those probabilities, right? So you and down the branch, so multiply down the branches, and then you add up the ends of the branches that you need. Okay. Let's do an example. Because, man, oh man. 3.43 is the one I want. Technically, what we're about to do is called Bayes' theorem. I'm going to show you the formula, and then you'll be grateful that we're not using the formula. We are in our heads, okay? But we're not going to use this. You could dissect it, you could pick it apart, and this is what we're about to do. It is called Bayes' theorem, but I don't like to call it that because we don't need to in this course. Okay. Just knowing how to solve it is good enough. Easier said than done, right? I'll start on a fresh page here. Jose visits campus every Thursday evening. However, some days the parking garage is full. Jose's lucky, he's got garages, but we get it, they're all full. Often due to college events. There are academic events on 35% of evenings, sporting events on 20% of evenings, and no events on 45% of evenings. When there is an academic event, the garage fills up about 25% of the time. But that's, so when there's an academic event, right? So it's conditional on there being an academic event, then we know the probability of the garage filling up is 0.25. And it fills up 70% of evenings with sporting events. And then on evenings when there are no events, it fills up about 5% of the time. If Jose comes to campus and finds the garage full, what's the probability that there is a sporting event? Use a tree diagram to solve this problem. Okay. First things first, right? We're given some conditional probabilities, right? When there is an academic event, then the probability is this, right? So that just automatically makes the parking garage outcome, right? Makes it the second thing, right? So the event, the type of event is going to be layer 1, right? And that takes practice to land on as well. But it's because of how the probabilities are given. So if we have 3 possible outcomes in the beginning, make sure you give yourself lots and lots of space here. I did not. Go one more. Like that maybe. And then I'll use A for an athletic event, S for a sporting event, and I'll use N for no event. Each of these happen with some probability, right? And of course, because these are all the possible outcomes, these should add to 1, right? So across the branches, we should always add to 1 or cluster of branches, you'll see. So A happens with a probability of 0.35. S is 0.20 and no events 0.45. So this is the event layer, let's call it. And remember, this drawing is just to help you solve the problem, right? If you feel like you could solve this problem without a tree diagram, I guess I'd be very impressed. I don't know how. Be a lot to keep track of. But then the second thing that we need to talk about is the garage. Now, on either of these days, it's either full or not full, right? So it's either full or not full, full or not full, full or not full. This might be a good time to mention that this is as far as we're going in probability. This is as hard as it's gonna get. It's hard though, so buckle up.
We could next semester.
No. And no. We've got bigger fish to fry. So when there's an academic event, the garage fills up about 25% of the time, which means that, okay, I could use all this fancy conditional probability notation, but really what I do is I just rely on the tree, making it obvious that, okay, well, 0.25, assuming I headed down the athletic event branch. Which means what? The probability that it's not full, if it's an athletic event, is 0.75, right? Because those have to add to 1. Right? Same thing with the sporting events. So 70% of evenings, so 0.70, which means 0.30. And only 5%, 0.05, make sure you get that 0 in there, otherwise it'll make a mess. And 0.95. So now I can go through and I can multiply down each of these branches, right? And I kind of shorthand these as AF, I guess. A and F, so an athletic event and it's full is, I'll do the math this one time, 0.35 times 0.25 is 0.0875, but then A and not full is 0.2625. I'm gonna need S and full is 0.14. S and not full is 0.06. And no event and full is 0.0225 because I've already calculated these. And finally, no event and not full is 0.4275. Right? If you add these up, they'll add to 1. And I guess we'll pick this up on Thursday. If you have any questions, let me know. Otherwise, I'll see you on Thursday.